Welcome everyone to the UCSD CSE database seminar. Today we have another exciting external invited speaker, Dr. Alex Ratner from the University of Washington and Snorkel AI. Alex has done some spectacular work, some groundbreaking work in formalizing and systematizing this so-called programmatic training data. So this is something that I have seen myself in several companies where they write heuristics and produce labeled data. And as we all know, labeled data is like the linchpin to modern AI. And so Alex has been working on some really cool stuff in the space on systematizing this whole process and has actually started a company around it. So a lot of fun, exciting stuff. And we are excited to have you here, Alex. Protocol for the talk, would you prefer questions during or at the end?
I'm happy. I'll save time at the end by default, but happy to take questions during. As you're familiar with, I've been talking about some of these concepts for a while, so it's more interesting, I think, certainly for me as well, if people interrupt and ask questions, and I'll try to keep it on track, but also would love to have discussion, but also otherwise save time at the end.
Sounds good. Okay, great. And audience, feel free to raise your hand, and either Alex can pause at an opportune time, or I'm happy to pause and get him to pause and ask questions. Feel free to also post it on the chat. So with that, let's get started. I'll hand it over to Alex. Alex, take it away.
Well, everyone, first of all, thank you so much for the invite. Thank you all for the time today. And I'm really excited, to share both some of the work that's been done in the past, some of the recent and more contemporary learnings from our work, actually a lot of it out in the field trying to apply it, and you have some discussion from there. And as Arun said, please interrupt with questions whenever it would be, there's anything. Otherwise, I'll save time at the end. And just as a note, I'm not monitoring the chat. So if you have something there, maybe Arun can pipe in, but otherwise just feel free to interject verbally.
Oh yes, so feel free to send the questions to me, and then I will ask that to Alex. That'll be easier. Thank you. Okay, sorry, Alex, go for it.
Awesome, great. So yeah, like Arun said, what I'm going to be talking about today, actually, over I'm going to be talking about some broad work, a lot of which was done at the Stanford AI Lab during my PhD, and then I'm also going to be sharing some kind of practical notes from the field about some work in the interim, both with applications kind of at Stanford and at with partner organizations on the academic side, and also taking in some learnings from the company Snorkel AI that's now building a kind of platform version of this Snorkel system that I'll talk about. And just again, we'll be kind of conversational here, so please definitely return the favor and interrupt and bring up any questions. Awesome. Okay, so I'm going to start with a little bit more motivation from the field than maybe in a standard talk about a new approach, just because I think it's interesting for the space in general. So first and foremost, the motivation that we started with around this project back in 2016 was kind of looking as really ML systems researchers and data management folks interested in where data management was accelerating or blocking the deployment of machine learning systems in the real world at where the bottlenecks were. And I'll give a quick caricature of a setting for supervised learning where at a macro scale you have kind of three major building blocks. You have some training data, so this is data that's labeled according to some kind of output schema that you want the model to learn to predict. You have some kind of model that's the actual parameterized function that's trying to learn from the training data so that it can predict an answer for new data points. And then you have, I guess, not just hardware, but also just in general, the infrastructure, both hardware and software layer that actually trains and then serves this model at test or inference time. So let's make this more concrete with an example. One recent publication we had in Cell Patterns with the Stanford and VA healthcare systems was around triaging chest X-rays and other medical images for basically physician assist. So imagine a binary classification problem. Chest X-ray comes in. We want to train a model so that it can actually just say, this is either an emergency, needs to be read urgently by a human, or it can sit in the queue, especially for, say, under-resourced hospital systems that have, large backlogs. So the interesting thing is that for a task like this is, an image classification task, the models and the hardware and the software infrastructure for serving these models in basic settings, I'm being a little bit glib here just to kind of provoke some lively debate later maybe, but really, for basic settings, they've never been more accessible and are arguably, at a almost commoditized status, right? If you want to, like our collaborators did, train an image classifier, the code for the model itself is a couple lines of Python. The compute servers to actually, train it over, fairly decent numbers of chest X-rays coming in is, fairly standard, right? But the training data, the data and specifically the effort to label it for this particular problem is the key bottleneck and differentiator. So just to give numbers on this, the modeling step for our collaborators on the radiology side took about 1 or 2 days of just downloading some open source models, some state-of-the-art models, training them, and actually, interestingly enough, between a bunch of the models we tried back at the time of the study, it was ResNets, DenseNets, ConvNets, if you're familiar with the image classifier space, all from standard open source libraries. And the difference in the metric we were optimizing, this is ROC AUC, was under a point. Conversely, labeling the training data took 8 person months of radiologist time, just clicking through, labeling examples, emergent, not emergent. And actually, the difference between a few weeks of that labeling and the full 8 person months was almost an order of magnitude greater than the difference in what fancy model architecture you used. So again, it's not to say that there isn't in any given application a ton of work to be put into the model, the hardware, the software, the infrastructure, et cetera. There's a lot of exciting stuff there that is going on and that needs to be done. But it's often so much more important to get the training data right and so much harder in terms of time in many settings. So we see lots and lots of settings where access to machine learning progress to all these great tools that are out there that are being developed and put into the open source every day are effectively blocked by the cost and the difficulty of labeling training data. And I want to go into some practical points that become especially salient when you're out in real world settings and deployments. First and foremost is the privacy. And so a lot of machine learning progress, if you actually look at the most celebrated and exciting examples, are based on public data sets and/or data sets that were labeled by outsourced process of sending data out to some Amazon Mechanical Turker or lay annotator who can then label it and curate this training set. You have something like ImageNet, where actually that even took years to build up, but you had the ability to send out to an Amazon Mechanical Turker somewhere in the world who would for fairly low prices label this is a cat or a dog or a teacup or whatever it might be. Most industries and most use cases, by many estimations, can't ship data out so easily. So when you work with finance, government, telcos, cyber, insurance, biotech, pharma, healthcare, anything with user data in the technology industry, you have much more stringent constraints, even for internal siloing and usage of data, and specifically around sending it out to be labeled. You also have subject matter expertise as a constraint. And so, if you look at the inter-annotator agreement rate for highly technical areas, for bioinformatics or medical or legal settings, even for experts who are highly trained both in the general domain and in the specific problem goals, there's often only 75 to 85% inter-annotator agreement. And so even for experts, it's difficult and very specific to the organization or the company. But in general, many problems, you need to have a fairly well-trained expert to even get to that bar. And so you can't just, again, ship it out to people who will kind of click cat versus dog. You need to have specially trained experts, often, again, internal for data privacy and expertise reasons. And finally, there's the issue of ability to iterate, right? So, there are classical paradigms in machine learning for how you adapt to kind of distributional shifts. There's online learning is the kind of most classical setting. But often what happens in practice is that you have very macroscopic changes to the input data coming in. often it's not just because the distribution of data changed over time, like the words people are using in social media drifts over time, and that's something that's been studied. It's often because one of many upstream teams or processes that is, pre-processing the data coming into your model changes. Someone changes how a word is what's tokenized or stripped of white spaces. This can throw off an entire model and really change everything. And then equally or more importantly, it's the fact that in basically every real world data science or machine learning setting I've seen, the output schema, the goals of the model are rarely fixed. Right? So we were working with a large US bank recently on a news analytics problem. Rather, they were using our platform Snorkel Flow. In a 6-week period, they changed the definition of what the model was supposed to predict over 7 times in discussions with their business partner team that was the downstream consumer. Similarly, we had a paper with Google recently where, again, you can probably guess that they have lots of budget for training data annotation, but even here they couldn't label it fast enough because of rate of change of the inputs and also the output goals. And so this ability to keep training data on-prem and in certain privacy silos, to have the relevant, often org-specific subject matter experts actually be doing the annotation and be able to rapidly adjust to upstream or downstream changes. This is what makes up the meat of this block around training data. Not just that you need humans to do it. It's these specifically that cause even some of the largest organizations in the world to really be just 0 to 1 blocked on training data. Now, one other quick kind of example that or one other way I'll phrase the motivation that's kind of coming at it from a different angle for the work on Snorkel and other techniques I'm about to present is this idea of how we've in machine learning to date, and arguably quite productively so far, completely decoupled the subject matter expert who knows about the problem, knows how to label it, from the machine learning developer or data scientist. And basically the way that you would have, let's take that doctor in the Stanford radiology example, essentially communicate or inject their information to the model is basically just, by passing, labeled data points, X, Y tuples to the model. And if you think about it, they often know, higher level patterns they're looking for. They see, oh, if I see this bright blob here, if I see the word malignant in the metadata of the nurse's report, then it should be, an emergent case. But they can't inject that information easily into modern model classes. It's almost like they're playing 20 questions or 20,000 questions to kind of communicate the pattern they're looking at that's informing their labeling to the model only via essentially single bit in the binary case, single bit, data points, one data point at a time. So again, this is great for machine learning developers because you can completely ignore and abstract away the messy realities of a doctor or a lawyer or a subject matter expert and just, take this massive question answer bank of lots of labeled data points and find the best model. But in real world settings, it's almost comically underutilizing what the subject matter experts know and their time for that matter. 8 person months of a radiologist sitting there clicking when they clearly know lots of richer domain information. So coming from both those angles, seeing the blockers and the nuanced blockers, not just around it being expensive, but around these privacy, expertise, and rate of change issues, and also just kind of thinking from the user perspective, from the human loop perspective, is there a better way for subject matter experts to interact? That kind of kicked off our efforts in 2016 to work on building a system and systems and approaches for raising the abstraction level 1 bit to asking users to programmatically label and manage training data. So to keep up with the toy example, imagine you ask the doctor to write those user-defined functions expressing what they're looking for in the image that would cause them to view it as an emergency. So this is an open source project. We were actively contributing up through around 2017, and then a lot of research up until, well, still ongoing around the project. Lots of great partnerships with users and sponsors. And then, I'm not going to talk much about this today, but I'll briefly mention that, on the, Arun mentioned we ended up spinning out a company in 2019, really because we saw that some of this is about algorithms that I'll talk about. A lot of it is about a kind of new human in the loop process. And, we wanted to actually put some engineering heft behind, the UI, the platform, the infrastructure to make this not just, performant, but accessible to subject matter experts, non-developers, et cetera. And that's a platform we call Snorkel Flow. It's, running in a bunch of exciting places now. So I'll share some experience, but I'll go back to more kind of talking about the academic ideas. And those academic ideas are mostly around this idea of programmatic weak supervision. The key idea being, building or rather, how can we build systems that enable users, especially, non-developers, subject matter experts, et cetera, to build and label and more broadly manage training data sets more, more automatically, more programmatically. Before I jump in there, does anyone have any questions around just kind of the motivation? I know I spent, probably more time than usual on a motivation slide, but wanted to share some of the kind of, recent, in the field experiences around that in particular. Any questions on that before I dive into the technical ideas?
Audience, any questions? I don't see any questions on the chat either, Alex. Okay. It was a very compelling.
One quick clarification questions about the motivation. So covariate shift has nothing to do with labeling data, right? It doesn't affect the labeling data. Whereas changing the outcome or the prediction problem would change the training data labeling process, but covariate shifts, I don't see the connection.
Well, if you have some kind of shift of the underlying data, then your model might become stale. Was the only point that I meant there, right? And I meant it only, maybe I'm missing the point, but I meant it only in a very simplistic way, which is that if your data drifts too much, then your model is no longer applicable to that data distribution, and then you need to, if you're just using a hand labeling approach, you need to go and just relabel a new data set. That's all I meant.
That makes sense. Thanks, Alex.
Yeah, but no, it's a good point. I mean, I think the more direct effect is in the output schema. It's also the one that I've seen relatively less work in the literature about on the academic side, but it's also just embarrassingly common where just someone says, I don't know, data science team trains a 3-way classifier, and then the hospital system or the bank business team says, no, we need 5 ways. And then, there's no real good way to leverage all the labeling effort you put in by hand, and you just have to start from scratch. So that's actually, to your, I think your point, the more interesting one, I think, because it's also just something that is ridiculously common in the real world, and I think fairly underemphasized in the academic literature to date. Anyway, so anyway, key idea is nothing push button auto magic. Really, just can we raise the abstraction level and change this into a kind of higher level and faster human in the loop process via this idea of programmatic training data management. So high level idea. I'm going to switch examples. I'll talk about just to keep it interesting and not at all because of my my slide hygiene. I'll switch to an example around document classification where we're trying to just basically say abstractly, like, classify a document, a legal document into, just a categorical classification problem. Is this a credit agreement, an employment agreement, something like that? This is just a concrete example of a document classification problem that I'll use as a running example for the next couple slides. So the first, kind of step in the Snorkel process, in some sense, the kind of, input, the key input shift is to ask users to, write what we call labeling functions. These are UDFs. They have, very simple semantics of basically each labeling function takes in a data point and either labels it or abstains. And so, for example, a user might say, I'm going to look for, pardon me, whether the word credit appears in the title or what I heuristically think might be the title. And if so, I label it, credit agreement, otherwise I abstain. These labeling functions can also leverage external resources, as I'll touch on later. And is actually, another kind of note from the field, kind of where it's very practically important, is it can, leverage external knowledge bases, ontologies, or dictionaries. It can use legacy systems. I'll come back to this point, but that's actually quite important in a lot of real world settings where you've put a lot of effort into, collating, organizing, building up information or prior systems around these problems that you'd like to leverage to kind of, not have to cold start your problem. But anyway, the advantage, or let me back up a step. I can't be overly negative. The advantage of these labeling functions is all the ones that you'd kind of guess fall out of it being this shift to code, right? You can label huge volumes of data with just a couple dozen or any number of these labeling functions that you could write in a small fraction of the time. You can go back and audit these labeling functions, which is quite important in a lot of real world settings. You can say what labeled my data set that then train this model to have this objective. You can version them, you can change them, you can reuse them across applications. But of course, the problem is that these labeling functions are generally expressing things that are heuristics or are noisy or poorly aligned sources of signal, what we often call weak supervision. And they'll, what this means is that they'll often be, far less than 100% accurate. They'll disagree with each other and conflict on data points. They'll be correlated potentially in odd ways. And all of this makes this kind of a tricky type of input to deal with. So more convenient in many very important ways, but also much messier. So a lot of the work that we did at Stanford was around this essentially modeling or kind of data integration problem around taking in these different labeling function outputs and figuring out how to combine them, integrate them into a single trained data point per label. Without going too much into the depth, although I'm happy to circle back around, the core intuition is building on very old intuitions, stuff that you could see in, say, the crowdsourcing work, or even far back beyond that. The basic intuition behind the algorithms and the theory is that you look at the agreements and disagreements between these labeling functions. So imagine I asked a yes or no. I asked, imagine all of you, had an accuracy. Some of you were adversarial. You were going to, lie more often than not. Some of you are telling the truth very often. And I ask a bunch of yes or no questions without actually knowing the answers to those yes or no questions. If I ask you enough of them, and you're not all colluding, or at least there's, let's say, 3 groups of you that are not, that are somewhat independent in your answers, not completely connected in some collusion network. Then I can ask you all these questions, and I could note, okay, well, Arun is tending to, agree with the majority, so I'll trust him more, and I'm tending to disagree with everyone else, and so I'll trust me less. And that's the intuition behind this. One of the several ways we've looked into doing this is actually basically this is materialized as looking at a form of the covariance matrix and doing a matrix completion style problem that with loose conditions will provably converge to the actual accuracies and correlations of the various labeling functions. Anyway, happy to go into that more depth, but I'm going to stay a little bit more high level and just talk about the rest of the process. So the key idea is once you've written some labeling functions that can label some portion of the data and then be kind of integrated and denoised in this way, you can use this to train a machine learning model that can generalize beyond the labeling functions. And so, one example, obfuscated but real world numbers is the labeling functions were actually quite good in this case. A lot of them are actually leveraging legacy heuristics that had been developed previously at this bank. And combined together, they were able to cover about 85% of the data. Once that was cleaned up by Snorkel, by the modeling part, we were able to train a modern machine learning, deep learning model that got 97%. So essentially, we were able to use these labeling functions plus a lot of unlabeled data plus Snorkel to train a model that could then generalize to do better on the overall data set. And the final step that I'll note, I'll come back to this a little bit, but at a high level, one of the most important practical things, especially with deploying this in the real world, is the ability to iterate quickly, to have a lot of guidance to a user, especially say a subject matter expert, of okay, your model is making these types of errors. How do you go back? Where do you go back in your data to correct and improve it or adapt it? Okay, so let me pause there and see if there are any questions on the kind of high level approach for programmatic labeling before I go into some case studies and just some kind of takeaway points from recent applications in the field.
Questions, audience? No? Okay, Alex, I have a question, but I think I will do it at the end.
Yeah.
Okay, that's
okay,
good.
Sure. I'll wait. I've learned that sometimes the awkward 5-second pause draws out some interesting questions or conversations. So it's a new habit I'm trying out, but we can also save all questions and discussion for the end. I think we'll have plenty of time. Okay, so jumping in, these are from some recent applications. All of these are from applications published in the literature or somewhere out in the open. So you can look into them in more detail if you're curious. I'm just going to kind of give a high-level overview and then just highlight some takeaway points that I think are interesting for this, both Snorkel and programmatic weak supervision in general, and potentially for more broadly for ML systems. So we did a publication and a set of projects with some teams at Google around a kind of proto version of Snorkel Flow called Snorkel Drybell at Google. The problem, as I mentioned, was actually that there was ample ability to pay for human labeling of data, but the problems changed too fast to hand label. And so we deployed, and we spent about 8 or 9 months building up a kind of internal system there around some of the open source ideas, and we were able to find that a couple of hours in Snorkel was able to replace tens to hundreds of thousands of hand labels. So if you look at this graph, the blue line is how just a normally supervised model would improve in performance as you add more hand labeled training examples. The orange line is just for a fixed amount of effort. I think we capped it at one day, so 48 hours of effort over a bunch of unlabeled data could perform. And you see that where they cross is effectively the amount of hand labeled data that Snorkel could replace. Now, of course, you can make the orange line go up as well by spending more human effort on writing and developing the labeling functions, but this is just one snapshot. The one thing I'll just mention here is that a takeaway for us that was quite interesting is that the speed of iteration and this rate of change of data is key, even in a setting where you have a huge amount of resources to hand label data. Even there, often you can't label data quickly enough if you have settings where the problem and the data are changing quite rapidly. Another point that I'll just mention as a takeaway point is we talked about the usage of or what we called organizational knowledge resources. So here, a lot of the labeling functions were actually leveraging internal resources at Google, things like topic classification models, knowledge graphs and knowledge graph based models, historical aggregate signals, a lot of different kind of existing functions or data sets were used and expressed as labeling functions to train up the final model we used. And so that illustrates something that then, since then, we've seen a ton with real users out in the field through the company and other routes where the ability to leverage existing information inside an organization, especially large ones, is incredibly impactful to making ML practical, rather than starting from scratch and hand labeling, say, a training set every single time. I mentioned this chest X-ray problem. Here's a visual of the results. This was about a few weeks of hand labeled data. This is the ROC curve for about I think this one was like somewhere between 8 and 14 person months of labeling. We had users sit down and write labeling functions, and after a couple of days of that, they got within a single ROC-AC point of the months and months of labeling. But how do they do this? Well, there's actually here kind of a trick. This actually was used in the Google paper in a different way as well, and this has to do with kind of leveraging paired modalities of data or paired feature sets. Simple example here. At test time, we have a chest X-ray or some image or let's just say some data modality coming in. We want to classify. Let's say image. At training time, however, we have both images, but we also have unstructured text reports in this radiology setting. So while we and some of my colleagues have done a lot of work on directly writing labeling functions over image and other data types, in this case, it was really easy for the radiologists to write labeling functions over the reports, the historical reports, but they were ultimately training an image model. So basically, you can ignore that like highfalutin way of saying it, but basically, this was a way of expressing domain knowledge, subject matter expert knowledge over one feature set, and then using it to train a model defined over a different feature set. In the Google setting, actually, we wrote about how we did the same concept, but instead of going from text to image, we went from what we called non-servable features, where the labeling functions used features that were private or were historical aggregates or slow or just not servable in production for some reason. Use this to train a model over features that met some SLA. Another kind of high-level takeaway, there's a recent result that I think was pretty exciting. This was just published in a blog post, I think, to date, but by my colleague Jason Fries over at Stanford, who's done some amazing work on various weak supervision techniques around especially clinical data. Here, he took Snorkel and used it to profile symptoms in EHRs for COVID evaluations at the Stanford Hospital. And one thing that was remarkable is that this system came out pretty quickly after COVID broke. And the takeaway I take from this is that one of the extremely kind of impractical aspects of machine learning in the traditional hand labeled way is this need to kind of requisition a new labeled training set every single time, a new data set per model. Whereas the reason Jason was able to respond so quickly is because he had a library, he had a software library, and so he didn't start from scratch. He was able to mix and match preprocessors and labeling function components to adapt to a new setting. And so that ability to kind of bring modularity and reuse from the software development world to training data and training data management is quite impactful in real world settings. Finally, one other just quick takeaway from some recent work that's out there. Some interesting work that again Jason and others and have been doing, actually, that we've seen on the company side as well with some of the government side work, is the use of expert knowledge, for example, in the form of ontologies, to supervise models via Snorkel. And so one technique that's actually worked quite well, both empirically and practically, is the ability to take an ontology to automatically decompose it into one or more labeling functions and use this to train a model. So imagine you're trying to label medical entities in text. You can use one of the many ontologies that basically catalog how different entities are referred to. In fact, these ontologies often overlap and disagree with each other. You can translate them into labeling functions, say pattern matching ones or other variants, and use this to train a medical entity classifier that actually uses the information from all of them. And I'll note that on a practical side, there's often actually both in medical as well as in, say, government or cyber settings, a huge amount of manual effort that's been poured into these ontologies. And it's almost ridiculous, again, to come in and say, hey, you should use machine learning AI. Why don't you throw out all that stuff? The NIH has invested hundreds of millions and even more on the cyber side has been invested, and just start from scratch, having your experts label data. The ability to leverage structured expert knowledge to train modern machine learning models is, again, both empirically but also just practically something that has a big impact. So again, those are just a couple of kind of more of the color of kind of notes from the field, takeaway points that are all motivated around the Snorkel system and deployments on the academic side. But I think that expose some things that are both failings of how machine learning is currently deployed, but also I think interesting kind of practical aspects that might be might spark other research ideas as well. So I'll pause for my 5 seconds just in case there are any questions, and then I'll go into a little bit of what you can do with training data programmatically beyond just labeling, and why I went out of my way to talk about building and managing rather than just labeling in the earlier slides. Okie dokie. So here I'm just going to give a high-level overview and actually, leave plenty of time for discussion, and I'm happy to go into more depth on this last part in particular if there's interest. But actually, in the last couple of years of research, we've looked at or we've kind of operated by a general heuristic of saying, I guess first premise of this broad body of work and the Snorkel system is, a lot of the success and the kind of high leverage points around machine learning systems today is in the data, and it's how it's managed more broadly, the training data. So let's try to abstract away some of the key operations that practitioners do on that data to get machine learning models to perform in practice and to manage them in practice, and see if we can abstract them away and then formalize them, build systems for them, build algorithms for fine-tuning them, etc. So the first operation in the supervised learning world, and the most obviously important one, and the one that I just talked your ear off about, is this idea of labeling data to train a supervised learning model, and that we abstracted as the idea of a labeling function. Data point comes in, output is a label. Another area that we looked at, I'll talk about in a second, is around what's often called data augmentation, the idea of taking some labeled data and transforming it or perturbing it to create copies, often to express some kind of invariance. We abstract this as a thing we call a transformation function. And also something I'll tell you about briefly called a slicing function, which tries to abstract away the operation of structuring or partitioning a training set into different subsets of relevance, which is again a common activity that you see in terms of getting machine learning systems to work in practice via the data. So I'll start with this transformation function bit. As a quick briefer for those who haven't heard of this aspect, one of the critical tools, but often the kind of, I guess, now it's gotten a bit more attention in the field, but back when we started looking at it in 2017, one of the kind of less kind of glamorous parts, unduly so, as I'll argue for briefly, of the machine learning pipeline, especially in the image domain, now also in text and other data types as well, is the idea of doing data augmentation. So the canonical example is, if any of you recognize that this is the MNIST data set, a canonical image classification benchmark data set, and the canonical example of data augmentation is, I take an example, say of a number 6 that's been labeled as the number 6, and I apply random transformations or perturbations that I believe should not affect the output label, that I believe express some kind of invariance that the model should ideally learn, say rotating and blurring and stretching and shearing and flipping, and I randomly apply them and I feed that into my model. So now I have a whole bunch of copies that are all labeled as 6, but are perturbed in ways that I want the model to be invariant to. Now the interesting thing is that if you look at, I'm jumping to another data set, we surveyed a bunch of them. You look at, for example, CFAR 100, another classic image classification benchmark. If you look at the top of the leaderboard, the difference in the top models is like tenths of a percent, or tenths of an accuracy point. The average accuracy gain from the top 10 CFAR 100 models from applying data augmentation versus not applying it was 13.4 points. So just a kind of very simplistic ablation study, but the impact of, again, how you manage the data, in this case, augmenting it, versus what model architecture you use is, vastly different, let's say. And not just, whether you use data augmentation, but how it's tuned and how it's, obviously there's a huge design space of what operations you should pick, how you should apply them, et cetera. So, we've done some work since then. One of the first pieces of work that we did was letting users write transformation functions that basically define kind of atomic incremental operations. From the perspective of weak supervision, here, rather than asking a subject matter expert to say, tell you a heuristic of how they label something, you're asking them to tell you a heuristic of something that they believe should be invariant about the data with respect to the classification problem. So, let's say, I guess number, single digit numbers, or I guess 10 is there. The numbers expert, or the radiologist in our real world examples that we studied, tells you, okay, you should be able to rotate, rescale, blur. We worked on various techniques for how do you now combine these. You can view this, just to give the nutshell idea, as learning a sequence of transformation functions to apply, which basically can encode in discretized form how much of each one do I apply, in what order do I apply when they're when the order is actually material, and then you can use this learned sequence or policy to actually train a model with a tuned data augmentation strategy. But again, high-level ideas, again, just saying, look, this data augmentation thing, like labeling, is often something that's just viewed as a pre-processing step, manually tuned, done ad hoc. Let's actually try to abstract it and put it on systems and algorithmic principles. And final one, I'll just give a brief preview of, that was some more recent work. It's around what we called slicing functions or slicing data sets. And so this slide is a little dense, but I guess let me take a step back and say, basic idea is in many settings in real world machine learning modeling, you don't have homogeneous data sets where you care equally about all parts of the data set and where all parts of the data set are equally easy or difficult. I'll stick more to the first example where you have subsets or slices of the data that you care much more about, or might be just particular error modes in your model. A lot of work goes on today around iterating on those slices, right? You have self-driving data set and you really can't mess up on yellow lights or stop signs. And you're having a lot of difficulty around stop signs covered in snow. Pardon me. Or you're training for a voice assistant and you really can't mess up on certain queries because they're controversial. How do you tell your model that even if those are highly minority subsets or slices, that it should really not mess up on those? Well, you can do all kinds of things like upsampling or upweighting, and but when you get to scale, this becomes very cumbersome and again very ad hoc. So in this approach, we again had users write something that was a kind of atomic operation here, what we call a slicing function that identifies a subset but doesn't say a label, just denotes a subset of importance heuristically. And basically, here's a little toy example where you have these sort of two areas of the data set where the decision boundary is not linear. They're kind of trickier, but let's say important areas to get right. And by telling your model to basically focus on these slices of the data and devote extra representational capacity, you can do much better. Anyway, all of that is basically just expounding on this broader theme of the ability to build and manage training data programmatically as a way to actually kind of put on good systems and data management principles and accelerate the types of activities that often have the biggest leverage in real world machine learning, and on the pessimistic flip side often serve as the biggest blocker to actually using machine learning in the real world. So let me now do a final stop there. That's the end of the main slides I have for today. I covered a lot of stuff at a high level. I'd love to either chat at a high level about some of the practical experiences and anecdotes, or to dive deeper into any of the topics I covered, or whatever you all would like.
Okay, thanks, Alex. More questions from the audience? Alex, do you have more slides you want to go through, or do you want to go into the Q&A?
I'd say go into the Q&A. Yeah.
Okay, let's go into Q&A. So let me get things started. I have a question for you. First of all, this work is spectacular, and it's also first of its kind that systematizes some of these practices that I've seen in various settings. I have two questions. One is, I guess, more philosophical than, I don't know if it's technical. So in machine learning world, they have these 5 tribes that Pedro talks about. And the symbolists have been around for half a century trying to write rules, to do labels, and they use that as the actual AI itself. And then came the statisticians, and then came the Pedros of the world who unified them into a Markov logic and stuff like that, statistical and rule plus breaking in these domain intuitions into the model itself. And then the connectionists have also been around, but really the power of connectionism was in the representation learning and the low-level representation learning from modalities that the symbolists did not care that much about, text and multimedia and stuff like that. And so going forward, so here what you have in the Snorkel worldview is that the training data is the distillation of the domain knowledge, which includes the rules and the knowledge bases and ontologies and stuff. And then the connectionist model or something else takes up from there. Do you see a future where all of that is fused and the training, I mean, training data is a means to an end for ML application in some sense. Can you see a future where all of those are fused and the model learns directly over disparate representations and the business rules and the ontologies? What is your take on that?
So first of all, it's a great question. I'm not going to have as good of an answer given such a well phrased question. But you know, that is very much the kind of, you know, so look, like one of the holy grails that like many people talk about, you know, ourselves included, is how to bridge between these two you know, worlds. I'll say, you know, a little, you know, I'll just call them, you know, heuristic based approaches and statistically learned approaches, right? Where obviously representation learning is a huge part of that latter bucket, and you could split them out. But just, you know, you have rules-based systems, you have, you know, machine learning, you know, or statistically learned systems. How do you kind of get the best of both worlds? And that's been a theme of a lot of work over the years. And it's obviously of a special interest now that, you know, on the one hand, you have extremely powerful and often, you know, pre-trained in some way, you know, statistical models out there. You have tons of data that they can learn representations over, either self-supervised or weakly supervised, for example. But on the other hand, they're also, you know, the trade-off, because there's never free lunches, they're increasingly black box. And so you have a lot of reasons why people are kind of yearning for the good old expert systems approaches, where you have, you know, the ability to audit, to change, to share, et cetera. And so, yeah, exactly as you said, Snorkel, you know, a big part of the motivation is just one way of bridging between the two, essentially with the data as the conduit, you know, taking your expert knowledge. And again, it's not all expert knowledge. You can have labeling functions that are machine learning models, but broadly speaking, you take your expert knowledge or your heuristics, you materialize them on, you know, a large volume of unlabeled data, use that to leverage either from scratch or pre-trained machine learning models, with the ultimate hope that you are, or let me be careful about this phrasing since we have a little time to talk. I'll say with the most exciting outcome, you know, being where, you know, your expert roles are able to specify some amount of knowledge precisely, along with the denoising and integration step that we have, and the statistical approach is able to do what statistical approaches are supposed to be good at, especially in the large data and representation learning settings we're in today, which is generalize, right? Now, a couple of notes there. One thing, since, you know, how I was kind of theming this is around practical notes, a big part of our design was motivated by practical considerations. One is just, you know, modularity with respect to the existing tools that are out there, right? There are a ton of, you know, machine learning models and ton new architectures coming out all the time. So we wanted to be very modular to that, right? This step of materializing on the data and then training a model allows you to be very, you know, modular in a very straightforward way with respect to all of the new models that are coming out, you know, every day on archive, right? The second thing is being practical around the fact that we really wanted to make this, you know, kind of a democratizing tool for data scientists. And honestly, one of the failure modes we saw most often when we do weekly office hours and workshops was, you know, people would be working on machine learning problems that, you know, really did not warrant, you know, a massive deep learning approach, let alone even a machine learning one. And so part of what we liked about this design is the fact that you can write some labeling functions, and essentially if that kind of rules-based or expert-based approach is good enough, you can stop there before proceeding on to machine learning, which is actually funny because on the academic side, in true fashion, I often get questions of like, well, gotcha, there's this data set where the labeling functions did super well and it disproves your method. And we're like, no, but that's actually like, that's part of the design principle. Like we started in the information extraction regime where usually you're trying to extract multiple things, many things actually from scientific literature and EHR or this, that, or the other. And so really you almost always have a long tail where you have some problems that are pretty easy. You'd like to get them out of the way heuristically first, and then devote your modeling time to the more complex ones. So that's just a little bit of practical color. The last thing I'll say is just a plug for some work that I'm not involved in, but over in Chris Ray's lab at Stanford, some recent work where they looked at other ways to kind of fuse the kind of expert and statistical based approaches of, say, can we take something like a labeling function and instead of, for efficiency reasons, training the model, just extend it with embeddings or something like that. Either way, you're kind of through that and many other approaches, and obviously Snorkel is one that we think is quite practical for various reasons and performant. But it's this idea of, can I bridge the generalization ability of the statistical learning, especially in today's environment, with the advantages of the expert-based approach.
Got it. Well, that was a very insightful and detailed answer. Thank you. Appreciate it. It is a fascinating space. Even in the deep learning world, a lot of the NLP folks, I don't know if you're you must be following that literature. They're baking in more structural assumptions into the model to make it more data efficient, to make it more parameter efficient and stuff like that. And so that's where the world seems to be heading in that landscape as well. So it'll be interesting to see how that pans out. Okay, I have more questions,
and
but
I think it's, I mean,
audience more chance to ask questions.
Yeah. The last thing I'll say, sorry, you're giving me too much bait for really interesting topics. I'll stay brief here, but just like, it is interesting. You see these cycles happening, and I mean, so some of it is like trying to find a middle ground, but there also seem to be cycles where it's like, okay, well, we can learn everything from the data, and then wait, but actually, if we can inject some of our knowledge and we can add more structure, and then suddenly you have that, and then someone, I'm sure at the end of the cycle is gonna be like, actually, we can learn all this from the data. And I think one of my hopes practically is that some of this like cyclical nature can be broken. I think one thing that people underemphasize in so many different areas is just, maybe it sounds really trivial to say, but the fact that like machine learning, I know it's appealing because of its generality. You can use one architecture on so many different problems and data types, right. But in the practical realities of machine learning, it's very segmented by use case. So some use cases, baking in these structural assumptions is great because you don't have a lot of labeled data, but you do have lots of structural assumptions. Other ones, just labeling data by hand and learning it all, still a very competitive and practical approach. Yeah, but anyway, I digress.
Sounds good. Questions from the audience?
One quick question, if there's another question.
I don't see any on the chat. Go for it, Baba.
Okay, so Alex, thank you for the great talk. So one quick question, can you also comment a little bit about the technical aspect of the denoising procedure? What are the assumptions that do we need there to essentially have any sort of guarantee that procedure converges to the true labels? It should be some sort of assumptions, I assume, right?
Of course. And by the way, also hi. It's great to see you at the new awesome post. Yeah.
Thank you.
So yeah, I mean, speaking a little bit high level, but kind of the core assumptions are you need to have first and foremost some way to break. Okay, so let me take a step back. First of all of this is based on a particular model of the labeling process, and so the biggest assumptions are baked into the way that you solve what is a latent variable model, right? So the classic models in the crowdsourcing regime, some of our base case models that I'll just segue into calling them labeling functions, are what's called conditionally independent. So it means that they basically make uncorrelated errors. The way I think about it, this is kind of a classic modeling setting, and obviously that's making a bunch of assumptions. It's assuming that also I can pull up some slides, but I hope I'll just keep barging on Fillmore. But it's assuming usually a global accuracy parameter. So it's not learning a data conditional model. It's not saying, okay, this labeling function is more accurate in nighttime versus daytime. It's assuming the labeling functions are not correlated in how they label. That's the kind of base model. And so then the two directions I just mentioned, we've worked on extensions there, as have some others. We've done a bunch of work on modeling correlations. This was just a salient aspect to consider if, again, if your labeling functions are written as code. Imagine I say, look for the word happy, and then labeling function 2 is look for the phrase very happy, right? Clearly, these are not conditionally independent signals. So being able to handle that more complex structure, being able to learn it even without labeled data is what was a big area of work for us. As was, as was and is, learning, okay, maybe I can't just have one global parameter for the labeling function. I want a model that it has different accuracies in different areas. Essentially, it has like an expertise area, right? Which is actually still ongoing work, I would say. So once you have, let's say this model where you have now not just conditionally independent labeling functions, but they could be correlated in different ways, right? Then we have two basic assumptions. One is that you have at least 3 cliques three connected cliques of labeling functions that are you can safely assume are conditionally independent. So intuitively, this means if I want to use that agreement disagreement type intuition, I can't have everyone in the room colluding on the answer. I need to have intuition. Think about 3 people. You have enough for a tie break, right? So again, we extend this to say that you can in fact have these correlations. We can even learn them from unlabeled data in a theoretically consistent way. But you need to have some degree of you can't have total correlation to be able to do this learning. The second thing is we need some way to break symmetry. Any approach here needs to be able to break symmetry. Think about to give the intuition there. Think about about like you are agreeing with the majority all the time, and Arun is disagreeing with the majority all the time over a bunch of data, where again it's not labeled. I don't know the correct answer, right? You could be 90% accurate or trustworthy, and Arun could be 10% trustworthy, or it could be flipped. And we need some fundamental way to resolve that symmetry. So what we do in Snorkel is we just make a practical assumption that's actually fairly flexible, especially with respect to other approaches. We don't assume that everyone is non-adversarial. We assume the majority of the labeling functions are non-adversarial, right? So we assume the user might write some bad apple labeling functions that even are more wrong than they're right, but we assume the majority of the labeling functions are good, that the user is trying, right? They're not adversarial, and that lets us break that kind of core symmetry. So those are the two kind of like fundamental assumptions, that and that you have enough unlabeled data, which is what our kind of sample complexity bounds characterize, at least for some theoretical guidance.
Thanks,
Great.
Alex.
Wonderful. More questions from the audience? So I have one more question, Alex, regarding the labeling functions. You deliberately chose to allow arbitrary code, right? User-defined functions, pure incomplete code, and that provides great flexibility. And that's very, you kind of agnostic to the specifics of the framework. In the rule-based world, and even in the MLNs and the kind of unifying of these different philosophies, they've kind of adopted logic or some other more restrictive mechanisms to reason about things better. What's your trade-off on this? So the more restrictive it is, the fewer opportunities you have to convey some domain knowledge. The more general it is, the less maybe people are inclined to provide information. What are you finding? Like if you ask people to write code, are you trying to layer out kind of abstractions on top of just having to write code? Are you trying to figure out other interfaces? Because I do remember you guys were working on some stuff like that, right? Yeah, no, it's a great question. And honestly, like, as you could imagine, this is like a typical start to an academic project. We had lots of more complex ideas about what the semantics would be. And we ultimately, to your point, ended up boiling it down to just a user-defined function that has an abstain, as one of its labels, right? And that ability to abstain actually is important. It sounds trivial. It's fairly important, the ability to say I don't know, and to have a notion of coverage of the labeling functions that helps allow the model at the end to generalize. But again, pretty much just said, look, throw in anything. And yeah, I think the trade-off is that obviously we were thinking about this a lot initially, even just about actually from the perspective of the subject matter experts. We were actually collaborating with a lot of kind of medical and biomedical and scientific folks at Stanford, and Python was a language where a lot of people could script in Python,
and we saw that number exploding, circa 2015, of even, people who had not described themselves even as data scientists or developers yet could write scripts encoding, a connection to a medical ontology or some heuristics in Python. So we said, okay, let's jump on this because we're trying to build a system for these kinds of subject matter experts. So I think the trade-off, is like, okay, if you have richer semantics, you can do more analysis, right? You could analyze, for example, if you have richer semantics, you could detect these correlations automatically without having to do a statistical approach, right? You could just, detect, you could basically have more sophisticated models of the labeling functions more automatically by leveraging those. And you could probably do a bunch of other stuff I'm not thinking about. But, on the other hand, we were just really taking a user-centric bet that the ability to just like dump in Python code would be helpful. And that ended up, I think, being one reason why, in the open source, some people were interested. Pardon me. And then, what we found, though, on top of that is though, and actually this is kind of the narrative that led to then spinning out the company, was that, really getting a Snorkel solution to work is not like, it's not like you wrote 5 labeling functions in 10 minutes and then you put this into this magical latent variable model that, as I just went through, is actually a fairly dumb model if you think about it. I mean, lots of extensions, but even with those extensions, still like a pretty dumb view of the world. You have arbitrary code being modeled as like, pairwise correlated, labelers with, maybe some feature conditional accuracies. Point is, right, it's not an auto magic approach. It relies on iteration, right? And so then exactly to your point, what we started to do with users, what we started to do when we did the deployments I talked about at Google or in the Stanford hospital and medical area, is we had to build templates on top and abstraction layers, right? And that's what you should get out of code, right? The point of going from like, zeros and ones of hand labeling to like, let's call it the machine language of just basic labeling functions, is you can then build abstractions on top. And so we started building abstractions on top, labeling function templates, labeling function generators, even natural language interfaces. My colleague, Braden Hancock, did some really cool sci-fi-esque work on. And now at the company, again, the part of the goal there was saying, look, like we've been told by a lot of our users that just having like a damn UI would be very, very helpful to be able to push buttons rather than writing the same Python code or not being able to because you're not a developer. And so that's one of the several directions that now, with a little bit more engineering attention, we're moving in, exactly to your question.
Got it. So you're doing that on the company side. Okay. Because I know like there are these labeling companies that farm out work and they have like text specific UIs and image specific UIs and stuff like that. So there is some work in the HCI world that you can potentially leverage to auto generate some of your labeling functions. Okay.
Yeah, no, there's super interesting work there too. And I mean, I'd love to see that some of that or I'd love to get more involved with some of that on the academic side as well. I think, to be honest, part of why we've done that in the company is because, a lot of it is not kind of like academically novel, so to speak. It's just, building the templates that are attuned to certain use case types, certain domain expert types, certain data types. Once you do that, though, it speeds up and improves the process quite a bit. And it's because then you're not just, again, like these labeling interfaces, you're not just saying, oh, now I'm doing text or now I'm doing image. You're doing, now I'm doing text and now I'm doing a certain set of labeling function templates, or we call them builders, that abstract certain types of signals that are most common, even some auto-generated signals, which gets into the kind of semi-supervised domain. Anyway, you get to the point where those kinds of advances actually have the biggest leverage if you quantify it than, say, improving the latent variable modeling another, delta or something. And that's been at least the real world experience that I've seen. Anyway, lots of interesting stuff.
Awesome. Okay, one last question. We are out of time. One last question. Anyone from the audience? I'm trying your awkward 5-second pause and it's not working. So I'm going to ask the question then.
The problem is that when it doesn't work, it's a kind of awkward backfire. But occasionally you get some really good questions from.
Speaking of not working, what happens when models fail? People try to understand and explain why models behave a certain way and stuff like that. And a lot of the literature in that space from the ML world and the explanations literature is data driven. They're like, oh, this is the part of the data that caused this, or this is sort of some stuff like that. And now in this sort of a regime where you have programs that have produced the training data, you have other knowledge bases and stuff that have produced the training data, do you see a way to explanations at a higher level?
Yeah, it's a great question. I'd still say it's an active area of work. I mean, I'm interested in it actively. There are a bunch of practical ways to do it. There are a bunch of, deeper questions to ask here. I'll say as a preface, I think that, model interpretability is a big, glorious mess right now, right? It's the kind of thing that as academics, we're super excited about, which means, there are lots of unanswered questions. And lots of great work there, right? But I don't think that's cut and dry. I think on the Snorkel side, there's a more limited form that falls out, in a very cut and dry, pragmatic way, which is just the ability to audit where the labels are coming from. So, as far as Snorkel goes, I'd say, interpretability. Again, I think that's a big area. So again, a lot of amazing work going there. I'll comment less. But a lot of, just keeping with the practical kind of real world notes theme of the talk today, I think a lot of folks actually are happy with just some way to audit. Okay, well, at least how did we label the data that trained the model to make this kind of decision, right?
Right.
And can we then go back and change it? And that falls right out of the idea of labeling with code rather than by hand. I will say, yeah, maybe there's some interesting work from some folks at Stanford on kind of influence functions and the ability to trace. This is Peng and Percy Liang over there. They one paper on the ability to trace errors in the model to particular training data points. Then they did a group-wise one, which they actually mentioned a connection to labeling functions of tracing to groups. So there's more interesting stuff there, I think. But I think even the basic step of just not being in this conundrum where you suddenly have a biased, either in the pernicious sense of the word bias or in the just local error sense of the word model. And when you want to go back and say, well, what happened? You have some gigantic data set of hand-labeled data points where you have no idea how to answer the question. Just going from that to at least you can look back at some code like you do with any other, malfunctioning software system seems to be a useful practical step.
Great. Sounds good. Sounds like there's a lot more fascinating research that intersects with your work in so many other areas. Okay, great.
So.
Thank you to the audience. Did anyone have any questions? I thought I heard someone ask a question. No? Okay, if not, Alex, we will switch to the other Zoom link. So thanks again for joining, and thanks to the audience for joining. Let's give Alex a round of applause, and we do that virtually these days. So that's your hand on the participants list. Thank you, Alex. Thank you for joining.
Thank you all so much for the time today, and for all the great questions, especially.
Thank you, Alex.
Take care. Bye.